Okay, welcome back. So we're just going to go through your book slowly, I suppose, and see what we're looking at when we're studying pattern. So in this chapter, you will learn to appreciate that processes can generate sequences of numbers or objects. If you know nothing about that, investigate patterns among these sequences. Just keep going. Use patterns to continue the sequence. Fine, which is if we have a pattern, 30 goes to 40 goes to 50, so it's called recursive. It's called recursion or recursive if we just can say wherever we are we can get the next term. So the term to term rule here is plus 10. And if you're going backwards, it'll be minus 10 because we'll be using that. But the term to term rule is add 10. But it's quite cumbersome and it's not very powerful. So if we could generalize, we could jump straight to term n without, we can jump straight to term n without having to go through all the intermediate terms up as far as term. That's what the general term is about. So I don't believe in studying these words before we actually use them. So let's jump in. So this is not a very popular type of question, but this is called clock mathematics. And the reason it's called clock mathematics, it's like a clock, things reset themselves every period. So if you go forward from right, you go, once you've done red, purple, green, yellow, then you've gone through a full cycle and it's going to start all over again. But this is like one round of the clock and it repeats. So this is called mod 4. So this is the shape of the 15th tile. And so you could switch over to camera and we're going to find out term 15. So we can just say, and I'm just going to scribble this down before you see what I'm writing, but I'm just copying it even though it's going to not have any color coding. Now there's two patterns there. There's the shape itself, and then there's the color. So you have a green triangle 3 in position 3, and you have a yellow hexagon in position 4. Here we go to the camera, and let's even make it more devout, more stripped of anything visual, and say it's a red triangle, it's a purple hexagonal, it's a green triangle, and it's a yellow. Is it a yellow square or a yellow hexagon? Yellow hex. Or visualize. Okay, but it's called mod format. What that means is that, or is it mod 5? Mod 4. You can get rid of 4, as many 4s as you want. So term 15 is equal to, now you go for a multiple of 4 below 15. And you subtract it away here. So what multiple of 4? 12. So term 15 is the same as term 3. So you take as many away as you can to leave your answer between T1 and T4 in this case, because we're doing mod 4 9. Okay, you can see it's a green triangle. Okay, but it's not very popular, so I'm just going to skip on past that now. So arithmetic sequences. Well, we certainly should do the work example. What else should we do? Only for sure the work example. Why not? It means we're anchored down and we know we've done what's in the book. And that's helpful. It gives us a sense of progress. I'll go back to single page FFAs. Let me just figure this out. And single page, and I think I'll try to superimpose my two images. I'll be a bit better. Okay. Reading is good, so I'm going to read to you. Arithmetic sequences can be used to predict real-life situations. For example, a taxi fare moves in an arithmetic sequence as the distance traveled increases. That's not a good example. That's continuous. The word linear is sometimes used instead of arithmetic. A sequence is a set of terms in a definite order where the terms are obtained by some rule. Again, not necessarily by a rule, but to typical things we deal with in maths, there is a rule. A number sequence is an ordered set of numbers with a rule to find every number in the sequence. Okay, so when we say there's a rule, there's two types of rule. Okay, there's the recursive rule, which can only tell you how to get the next term, and then there's the general rule. You can get the value for any one term without worrying about the values up to that. Okay, so there's the recursive rule, or the term-to-term rule, and then there's the general rule. In an arithmetic sequence, the difference or change between one term and the next is always the same. An arithmetic sequence is also sometimes called an arithmetic progression. In the arithmetic sequence 2, 6, 10, 14, 18, the difference between consecutive terms is 4. The difference between consecutive terms in any sequence term n is referred to as the first difference or the first change. In an arithmetic, you don't see that often, I've never seen that, I think they might have made that up. In an arithmetic sequence, the first difference is constant, and it can also be referred to as a common difference. But because it is constant, it's common. The letter D is used to represent the common difference. It's actually used to represent the difference regardless. The two sequences shown below are arithmetic. Okay, you have a difference of 7, it's going up by 7, and you have a difference of -3, meaning it's decreasing by 3. Okay, there's a graph of an arithmetic sequence, and this is a kind of a pattern that keeps expanding with a kind of a rectangle missing in the middle. And the way you can identify that that's arithmetic is that it's really about perimeter. It's not about area. Anything to do with area or two-dimensional will be quadratic, so I'll teach you how to spot them as we go. Okay, so anyway, let's do some work here. Some more paper. Okay, so let's say for each of the following arguments, write down. Okay, the question is the same all the time. We're just analyzing the situation. So I'm just going to analyze. It'll take all the burden of reading the question out of the way. Right. So ignore the left. Just go for the question bit here. So we have 1, 5, 9, 13. 5 take away 1. So take your pen, start here, mark back 4, 4, 4. Work out what will go here. Take away 4, 5, subtract 4 is 1, 1, subtract 4 is -3. Okay, which brings us to term n. Write down the formula, by all means, is equal to a plus n minus 1d. And don't do any arithmetic, don't do any algebra on it. Just that's the formula. But that formula and this same thing. So we got 4n minus 3. Okay, you can use that to work out any particular sequence. Another worked example. Now, so here what we're going to do is the question isn't going to give us any numbers at all. It's just going to give us the pattern. So we can clearly see this here is 6. this here is the original 6, but we're adding on 2 and add on 2 again. So it's our arithmetic sequence. Okay, with a 2 and a 2. Now, they'll often ask you to plot the next term. Okay, so I'm going to do that here. There were 2 dots in the middle, and then we went with 1, 2, 3, but we're going to add another 2. And that'll be 12. Okay, draw the next 2 patterns. Fine. And we can draw another one again, no problem. And they'll usually give you a nice bit of space and everything. I just ran into a bit of trouble here. Not space. Count the number of dots in each of the first 5 terms and display the results in a table. Don't worry about the table thing, just put them across the page. And the only thing here you'll be saying is this is term n. You'll be adding in n. There's 1, 2, 3, 4 going on forever. Okay, but don't worry about it. Your tables can be very flexible. They can work vertically, they can work across. You can just say, you know, once you have a row of numbers, then that is a table. You can add in another row, and you can put your headings in the table. Describe the sequence of numbers generated by the pattern. So essentially, you can describe it with start with 6 and keep adding 2. How many dots are there in term 7? So, is that term 7? Yeah. So, we could count up along. It's just about manageable. 6, 8, 10, 12. 14 is the 5th. 16 is the 6th. 18 is the answer. Okay? But we're getting to the edge of what's acceptable in terms of exhaustion or recursion. Okay, because that was quite a lot. It would be far better to do it this way. How many dots are there in the term n? So the one back will have 4 in it. And this is 2, so term n equals 2n plus 4. And that's the answer there. Now state, given your reason, whether or not the following are arithmetic. Okay, I can see a difference of 2, yes. Or state, giving a reason. Always give the same reason. First difference is a constant. 2, 4, 6, 8. Yeah, we're skip counting. Anything skip counting is definitely arithmetic. 1, 2, 4, 8. No, we're doubling, so there's a no to that one. 1, 1, 2, 3. On here. So add. Yeah, that's the Fibonacci sequence. The first 2 terms are just given to you before you really start creating anything. Then you add the previous 2 terms. You get 2. 2 and 1 is 3. Okay, it's not like it's not arithmetic, it's not geometric. If you were to do first difference, you won't be happy. You get 0, 2, 2. You might think you're on something here. Next thing it's 3, and I think this will create another sequence that looks very, very, very similar. Okay, and that'll bring me up to your homework this evening, which is these. I'm not saying we're going to do them all, we'll do a few of them and I'll post this on YouTube. It's 13 minutes long already, but that's okay. It takes a bit of time to practice and absorbing concepts. Looking at all the problems come up in problem solving. Problem solving takes time. Okay, so let's just jump in. The questions won't really matter because we do them anyway. Okay, so I'm really just interested in analyzing and solving the situation. Some of these you could do by looking at them. The minute you notice differences, 2, you have 2n plus 3. You have 3n because it's going up in 3s, and if you go 3n plus 1. Oh, something else I'm going to show you. So you see you've got your 4, 7, 10, 13. Watch this. What's 4 and 10? 14. What's half of that? 7. What's 7 and 13? 20. Half of that is 10. Okay, well, why is that handy? Because it will allow us. So I'll just show you another way, obviously, another way of getting this term 0. Okay, now this takes careful thinking. This is called mathematical thinking, a mathematical progression or how one thought leads to another. So it's very, very important, because this type of thinking is what gets you, is what happens during your exam. You're going to have to think if they're always coming up with original questions, more or less with the core skills, but you still have to look at a situation you never saw before, because they're very, very good at that. That's project math style questioning. Okay, so let me just say that this is term naught, and say 7 and term naught is equal to double the middle. Now let's make term naught the subject of the formula. We want him in his own, so leave him where he is. And you get 2 times 4 minus 7. Okay? So in other words, double the first and take away the second. Double 4, 8, take away 7 is 1. Next sequence. 1, 5. Don't worry about the bother with commas. You don't need them if you leave a good space. Okay. So certainly I can see that it's 4, and certainly 1 take away 4 is negative 3. But double this, 2 take away 5 is negative 3 as well. Double the first, subtract the second. I'd argue it's more difficult, but one way or you get minus 3. Term n equals 4n take 3. And if you put that in the table in your calculator, you're just going to regenerate what you knew already. And quickly, maybe less talk. This thing is tiring. Well, I don't know if it's close, but it is close. 13 take away 7, 6. Just before I commit to writing it down, 2 13. Don't know how long it's been like that for now, but I'm going to drive on. And 2 13s take away 20 is also 6. Get the 6 here from under watching. It's nice to have an alternative way of calculating something. So 7n plus 6. Now a decreasing function, be very careful with these. I'm just going to take out my calculator and be extra careful about the subtraction I need to do. Okay, calculator on. We always start here. We subtract it. So I'm doing 57 subtract 59. Negative 2. Okay, it might have been easier without the calculator to say I'm dropping 2, dropping 2, dropping 2, dropping, decreasing by 2 by inspection. Okay, so increasing by 2 as we go this way. And indeed, you could just go, and remember, every time you pick up your calculator, it doesn't matter how big the numbers are really. 2 multiplied by 59, take away 57, equals 61, or add 2 and you get 61. So term n equals minus 2n plus 61. Okay, just want to see if there's anything particularly challenging on the far side. The only thing is we're dealing with negative numbers, but it won't be a problem. Okay, so minus 12 minus 7 minus 2. But just in case we're getting a little bit mentally tired in terms of what's going on here, we can just pass it all to the calculator. Minus 7, and no, if anyone ever told you can't do minus 1, it's just not true. Minus 12 equals negative 5. Do that wrong. Okay, which is enlightening. So let's look at it. We went up 5. We went up 5. So it is an increasing thing. But and that should have come from, let's get my bearings here. 59 subtract 61 is minus 2. Yeah. Oh, I forgot the minus. I should have gone minus 7 minus 12. Try the other thing. Double the first. 2 by minus 12. Minus 7 is the same as plus 7, and we get negative 17. Minus 12 minus 5. Yeah, I might have got a little bit distracted there, and this can happen to anyone. You think you know something very well, and that's why I'm always saying about over-learning or deep learning in order to really remember stuff. Apologies for focus again. Bring it back here now. And so that is 5n minus 17. I'm trying to do it quickly now. We're going to do it quick in short order. 43, 40, 37. Minus 3, minus 3. Double the first, take away the second. 86, take 40, 46. Or plus 3 to this 46. Put that in a box. So that's probably enough for today. It might be a long video. It is 20 minutes long. But hopefully you enjoy it. I'm going to fire it up on YouTube. 3 or 4 people, or maybe my whole class will look at it. As always, students, I will see you in the next one.